Assalamu alaikum. Welcome to the next topic. In the previous class, we discussed about the algorithm or summary of the Gauss-Seidel method. Today, we'll do it. We'll do the same for the Newton-Raphson method. That is the algorithm of the Newton-Raphson method. So the first step is the data reading, which is same as that of the GS method. That is calculation of. I just have a look at this. Now, this data reading, number of buses, line, generator bus, and load buses, formation of Y bus. V1 delta 1 for the slack bus, PI for the PV buses, where I goes from 2 to N, PI for the PQ buses, where I goes from N plus 1 to N. Initial case for unknown, that's delta I is equal to 0, Vi is equal to this one. This is for I is equal to N, this is for I is equal to N plus 1 to N. So reactive power limits has to be known. That is reactive power limits for all PV buses and voltage magnitude limit for all PQ buses. This is the data reading step. After that, we have for this Newton-Raphson method, we have to calculate the real and reactive power mismatch. That is delta Pi R plus 1, which is equal to Pi specified minus Pi function of delta N V, which is nothing but the summation of Vi into summation Vj Yij cos of delta I minus delta Ij minus theta Ij. This is that term. So here I will be equal to 2 to N for all PV and PQ buses. Delta Q, that will be equal to Qi specified minus Qi, a function of delta and V. And here I will run from M plus 1 to N for, that means for all PQ buses. And after that we will calculate the maximum of delta P and maximum of delta Q. That will be the maximum for all these values will be taken as the maximum delta P and maximum for all the reactive power values. Reactive power mismatch will be taken as delta Q R plus 1. Now here stopping criteria will be checked at the third step, not at the last step, because if delta Pi and delta Qi, that's maximum delta Pi and maximum delta Qi is less or equal to some stopping criteria, that's epsilon, and this Qi is also less or equal to some epsilon stopping criteria. That means if the above conditions are satisfied, then stop the calculation and compute the slack bus power, line flows, and power loss. If not, then we have to go. If not, then we have to go to the next step. And what we do, we calculate this delta R and delta VR, which is equal to JR inverse delta PR into delta QR. After calculating this, we'll calculate the updated value of delta and V, delta R plus 1, VR plus 1. We know that what is the order of this matrix, The deltas are all the deltas from 2 to N. This V is all the voltage of PQ buses, that is from M plus 1 to N. So this will be equal to delta R, that's this value, previous value, plus the calculated value of the mismatch, that will be updated value of the all the variables. So the next step is calculation of Pi and Qi for all PQ and PV buses. Now after that, this checking of Qi for variable, this reactive power limit, this is almost the same that we have done for the GS method. So here I will run from 2 to M, that is this has to be checked for every PV bus. So if this is equal to this, then it's a PV bus, and Qi R plus 1 will be same as Qi R plus 1. We have to take it, the value which has been calculated from the different values of the variables. But if Qi R plus 1 is greater than Qi max, then we have to take this value as Qi R plus 1, not the value which is greater than this. So that is Qi R plus 1 will be then equal to Qi max. If Qi R plus 1 is less or equal to Qi minimum, then Qi R plus 1 has to be taken as Qi minimum, not the value which is less than this. So during this iteration, if any one of these two equations occur, then we have to consider it as a PQ bus. Now similarly, checking voltage for its limit is the same as that of the step 5 of the Gauss-Seidel method. It will be identical of that method. So after calculating this, then we have to go to the step 2, that is this step, and we have to compute it and calculate it accordingly until the stopping criteria will be met. So this is the algorithm of the Newton-Raphson method. Now let us try to have a comparison between the two methods. We'll have parameter Gauss-Seidel method and Newton-Raphson method. Time for each iteration. You'll see that it will be less in Gauss-Seidel method, but it will be more in case of Newton-Raphson method. How much? That is 7 times. So for a simple iteration, Newton-Raphson method takes more time to do one iteration as compared to the Gauss-Seidel method, because we need to calculate the Jacobian elements in each iteration. Complexity of the each iteration is here, it is less, it is more. Again, the reason is same. Conversion rate, it is slow, it is fast. It is because of this that is it is preferred over this Gauss-Seidel method. Convergence rate, slow and fast. Type of convergence is linear and quadratic. It's a mathematical term, we don't have to go there. Accuracy, Gauss-Seidel method has less accuracy, Newton-Raphson method has more accuracy. So suitability, Gauss-Seidel method is suitable for small power systems, and this Newton-Raphson method is suitable for large power systems. Number of iterations required. The number of iterations required increases with the number of buses. It is fixed around 3 to 5. It will not change if the number of buses increases. Here the number of iterations required for the convergence, here it remains fixed from 3 to 5. Also, the convergence is dependent upon the selection of the slack bus and the presence of series capacitor. So, but this Newton-Raphson method is independent of the selection of the slack bus or the presence of the series capacitor. The convergence will not depend upon these considerations. Complex form. Usually we use the complex form as rectangular form in Gauss-Seidel method, and in case of Newton-Raphson method we use the polar form. There are certain advantages, we will not go into that, but this is usually the case. So let us now come to the decoupled Newton-Raphson load flow. In this case, what we do, it is also known as approximation to the Newton-Raphson method. So we take the advantage of the actual power system, because actual power system, you will see that our system is designed in such a way so that active power is sensitive to the change in phase angle and insensitive to the change in voltage. Also, the reactive power is sensitive to the change in voltage and insensitive to phase angle. That means delta P by delta will not be equal to 0. It will have some value. That means change in power with respect to delta will have some value. Similarly, change in power with respect to voltage will be close to 0. It will not change with when voltage is changed. Similarly, the reactive power when changed with respect to voltage will not change. Similarly, this reactive power will change. Reactive power with respect to this delta, it will not change. This can be shown from this diagram. We have a simple 2-bus system. Here, let us say we have the voltage at this bus is equal to V1 angle of delta. Here, the voltage at this bus is V2 angle of 0. That is the reference to take in this bus. So the line has an impedance of X. So when we calculate the real power at this bus and reactive power at this bus, it comes out to be V1 V2 by X sine of delta. Here Q2 is equal to V1 V2 by X cos of delta minus V2 square by X. We'll derive it. So for the time being, I have written the direct equations. For practical power system, delta is very small, around 5 to 10 degrees. So sine delta will be equal to 0 and cos delta will be close to 1. So let us first calculate delta P2 by delta. It comes out to be equal to V1 V2 by X cos of delta. So it will be equal to close to this. Since this cos of delta is equal to 1, this will be V1 V2 by X. This is not equal to 0. It means there is a change in real power with respect to the change in delta. Similarly, change in real power, will calculate change in real power with respect to voltage V2. It comes out to be V2x by sine V2x into sine of delta. Because sine delta comes out to be close to 0, this will be close to 0 since this is equal to 0. That means the change in real power with respect to voltage is close to 0. Similarly, delta Q2 by delta will be equal to 0. Same reason, differentiating with this with respect to delta, and then putting the value of cos of this sine delta equal to 0, you'll get to will be equal to 0. Similarly, delta Q2 by delta V2 will be this equation. So this is not equal to, again, this is not equal to 0. This will have some finite value. Again, we can see that reactive power changes when the voltage is changed. Coming back to this equation, now this is the usual equation of our Newton-Raphson method, which is not decoupled. So delta P, delta Q, delta P by delta delta, delta P by delta V, delta Q by delta delta, and delta Q by delta V, delta delta and delta V. Since we know that from these explanation, this is 0 and this is 0. So this matrix reduced to this. And when we multiply it, you will see that delta P will have only delta P by delta delta multiplied by delta delta. There will not be any delta V, because delta V will be multiplied to this 0. It will be cancelled out. So the total equation will be now, that means delta P will be equal to delta P by delta delta into delta delta. That is this, when we multiply delta P is equal to delta P by delta delta into delta delta. Similar, delta Q will be equal to, this is 0 plus delta Q by delta V into delta V. So the two equations will be like this: delta P is equal to delta P by delta delta into delta delta, and delta Q will be equal to delta Q by delta V into delta V. So the order of this will be n minus 1 cross 1. Order of this will be n minus 1 into n minus 1. Order of this matrix will be n minus 1 cross n, 1. Similarly, order of this will be n minus m into 1. Order of this will be n minus m into n minus m, and order of this will be n minus m cross 1. And from here, we can assume that this J12 will be equal to 0. That is, this matrix J21 will be equal to 0. You can see it over here. This is actually J12. This is J22. There will be no term at J11 and J12 and J21. So I will expand this term as like this: delta P2, delta P3 up to delta Pn, because these will be all the real powers from for all buses except slack bus. So again, delta variables will be delta 2, delta 3 up to delta n. That's all the deltas which are unknown for all the buses except slack buses. It will be n minus 1. So its order will be n minus 1 cross 1. Its order will be n minus cross 1. So these terms will be all the equation, that is all the equations which are derivative with respect to all the variables. So this will be delta P2 by delta delta. That is the first equation, which will be derivative with respect to all variables. It will be delta P2 by delta delta 2, delta P2 by delta delta 3, that is up to delta P2 by delta delta n. Similarly, this is the second equation, that is delta P3, and it is derivative with respect to all the variables. All the variables are deltas. So this will be delta P3 divided by delta delta 2, delta P3 by delta delta 3, that is up to delta P3 by delta delta n. So this is the last equation, derivative of the last equation, that is delta Pn, and this equation is derived with respect to all the variables. This is delta Pn by delta delta 2, delta Pn by delta delta 3, derivative of delta Pn by delta delta n. So this is our first matrix equation. You can see delta P is equal to J11 into delta delta, and we now know the order of all the matrix which are in the equation. Similarly, for J22, delta Qm plus 1, that is all the mismatch, reactive power mismatch of the PQ buses, and we know the PQ buses will start from m plus 1 to n. So delta Qn plus 1, delta Qn plus 2 up to delta Qn plus 1, delta Qn. So its order will be n minus m cross 1. So variables will be all the unknown voltage of the PQ buses. That will be delta V m plus 1, delta V m plus 2, that is up to delta Vn. Its order will be n minus 1 cross 1, n minus m cross 1. Similarly, for this, all the equations which are n minus m, and all the variables which are n minus m, so order of this will be n minus 1 cross n minus m cross n minus m. So this is all about the decoupled Newton-Raphson method. Using the decoupled Newton-Raphson method, we'll solve the numerical which we have already solved. So total number of buses we have 3. Bus number 1 is the slack bus, bus number 2 is the PQ bus, and bus number 3 is the PV bus. So the variables will be delta 2, delta 3, because both deltas are absent, and V3. Given will be P2, P3, and Q3, because for PV bus, PQ buses, PQ and P2 will be given. Also, Q2 will be given for PQ bus. So, as we know that we have calculated its matrix, total matrix will be like this: delta P2, delta P3, delta Q2, and these are the Jacobian elements: delta P2 by delta delta 2, delta P2 by delta delta 3, delta delta 2, delta delta 3, and delta. These are the variables that should be delta V2. Since when we use the decoupled neutralization method, we know that delta P2 by delta V2 will be equal to 0. This will be also 0. This will be also 0. And this will be also 0. This matrix will be G11, 0, G12, G21, 0. So that means it will be reduced now to this matrix: delta P2, delta P3, delta P2 by delta delta 2, delta P2 by delta delta 3, delta P3 by delta delta 2, delta P3 by delta delta 3, and then these two variables, delta delta 2 and delta delta 3. I have written it like this: delta P2, delta P3, delta P2 by delta delta 2, delta P2 by delta delta 3, delta P3 by delta delta 2, delta P3 by delta delta 3 multiplied with its variables. That is delta delta 2 and delta delta 3. Similarly, for this case, delta Q2 will be equal to these two will be 0. It will be delta Q2 will be equal to delta Q2 by delta V2 into delta V2. It's not V3, it is V2. That is written over here. Delta Q2 is equal to delta Q2 by delta V2 into delta V2. This will be 2 cross 1, this will be 2 cross 2, this will be 2 cross 1. All of these matrices will be 1 cross 1. Now, given the values of which we have already calculated from the previous numerical, that is this is delta P2 by delta delta 2, this is delta P2 by delta delta 3, delta P2 by delta P3 by delta delta 2, delta P3 by delta delta 3. When we put these value in these matrices, so this delta delta 2, delta delta 3 will be equal to 24.47. You will see that this matrix, this matrix will be there now. That is the only given one. That is the 4 elements of this matrix will be now there. I have written them here, and only these two values, that is delta P2 and delta P3 will be there, which will be multiplied to this delta P3. And when we multiply it, we get delta delta 2 is equal to this value, delta delta 3 will be equal to this value, and delta V2 will be equal to inverse of this. That will be equal to 1.96 divided by 22.54. So you can see 1.96 divided by 22.54 is will be equal to 0.0869. So when we get the updated value, you will see that delta 2 1 will be equal to delta 2 0 plus delta naught. This value will be 0. It comes out to be 0 minus this, that is minus 0.0034 radians. Similarly, delta 3 updated for first citation will be minus 0.066 radians, and V2, this should be 1, sorry, V2 0 plus delta V2 0 will be 1 plus 0. And the values which we have already calculated, you will see that it will be very close to the one which we have already calculated. Okay, only this one will be, and definitely it will be slightly deviated from the values which we have calculated with the exact Newton-Raphson method, because we are using the approximation. So by using that approximation, this type of Newton-Raphson method, which is known as decoupled Newton-Raphson method, will take more iterations to converge as compared to the Newton-Raphson method, which is the exact one. So I hope you understood this. So with this, I will stop this this power flow analysis or load flow analysis. I will start with new topic, that is the Power System Synchronous Stability. This is the new topic and new unit. So first we will see what will be the stability. Stability in layman's language is nothing but, we can say, it is a maintaining the synchronism. Since it is related to the synchronous stability, so it is usually related to the synchronous machines. So a system, since we know that our power system contains a number of synchronous machines, all the generators usually are synchronous generators. So we say that the system will be, or our system will be stable only when the synchronous machines are running at the synchronous speeds. So in other words, we say that maintaining the synchronism means that our system is stable. In all cases, all the interconnected synchronous machines should remain in synchronism if the system is stable. Because we know that we have different types of machines, synchronous generators, which are connected in parallel to supply the real and reactive power. The system will be stable when they are all running coherently with each other, or we can say when they are running uh, with each other at synchronous speed. So loss of synchronism or falling out of step means instability. If the synchronism is lost, we say that our system has lost the stability. It is an unstable system. So what is the definition of stability? The stability of an interconnected system is its ability to return to its normal or stable operating condition after having been subjected to some form of disturbance. So we know that our system, when running in the normal condition, we cannot say it's stable or not. This stability actually is connected or concerned when some disturbance occurs. And that time we could analyze whether the system is stable or not. When the disturbance occurs on the system and it comes back to its normal state or other stable operating condition, but again it is stable, that means it is running now after the disturbance is over, it is running at synchronous speed, we say that the system is stable. If because of this disturbance the synchronous machine is not running at synchronous speed, that means the system is not stable. So the form of disturbance may be quite high, maybe quite low, maybe slow, maybe fast. Based on the form of disturbance, the stability is classified into three types of stabilities. So one is steady state stability, another is transient state stability, and the last one is dynamic stability. Steady state stability means the ability of an electric power system to maintain synchronism between the machines within the system and an external tie line following a small slow disturbance. So we'll not go into the tie line. What does this tie line mean? Actually, this tie line is nothing but a transmission line connecting between two power systems, which are two different power systems and which are very far away from each other. When a line is connecting between these two, we see that type of line which ties the two power systems are known as tie line. So in this case, again, the steady state stability means a system regains its stability or its normal operating condition when the disturbance is small and slow. Such type of this stability is known as steady state stability. The small and slow disturbance may constitute normal load fluctuation, the action of AVR and turbine governor. So this small slow disturbance may be because of the load fluctuation, which are the normal load fluctuation, action of AVR because voltage may change and AVR may increase or decrease the voltage as per the voltage requirement, and turbine governor. Turbine governor also open the valve to this turbine or close the valve to the turbine. That is done so as to have a desired value of the real power. The steady state stability limit, that is the limit, refers to the maximum power which can be transferred through the power system without the loss of stability. So there will be a limit, and that limit we can say that this is the limit of the power which can be transferred to the from one end to another end of the transmission system, and this limit will not, this is the maximum value beyond which if we transmit the power it will result in the instability of the system, or up to that point if we supply that power to the system it will not, it will come back to the synchronous or the normal operating condition or steady state operation condition. So this is known as steady state stability limit. Is the maximum power that can be transferred without losing the stability in general. So system nonlinearities are generally ignored in steady state analysis. The study time for steady state analysis is usually few seconds to several hours. So this is for the steady state analysis. Now the second one is the transient stability. The transient stability is the ability of the power system to maintain the synchronous. You will see that this definition is same as that of the steady state stability, but following a large disturbance. Here the disturbance is large and maybe fast. Large disturbance include faults. Fault is a large disturbance because uh, it results in the change of bulk load. Bulk load change means because in the normal operation condition, a load may be supplied to the system. When fault occurs, all the load will be shut down to zero. So clearing of faults is again opening of the circuit breaker. It results in the decrease in the load, and it will be a large disturbance. And when we close this circuit breaker, a large load will be applied on the system. Is again a large disturbance, large load change. Sudden change in the bulk load and tripping of the lines and generators. This also results in a large disturbance or large load change on the system, which can be taken as a disturbance and which may result in the transient stability. Again, transient stability limit refers to maximum power which can be transferred to the system without a loss of stability under certain large disturbance. So, like we have the steady state stability limit is the maximum power that can be transferred without losing the stability. We have transient stability limit, that is the maximum power that can be transferred, and the maximum power is transferred or changed simultaneously, not slow or this small power. So it is to be changed in bulk, and the transient stability limit offers that bulk maximum power which is changed in bulk. When that is transferred without the losing of synchronism, we say that that refers to the transient stability limit. You will see that transient stability limit is always less than that of the steady state stability limit. So I will show you how this is less, but for the timing you should just keep it in your mind that transient stability limit will be always less as compared to the steady state stability limit. System non-linearities play a vital role in transient analysis. The study time is less than 1 second. So this is the transient analysis. Dynamic stability, the ability of the power system to remain in synchronism or to be stable after the initial swing. This transient stability period after the transient stability period is over until the system has settled down to a new steady state equilibrium condition. So dynamic stability actually refers in the time domain after the transient stability period is over. This actually stability is similar to that of steady state stability. In that case, we see that whether the system regains stability or not when the power change is slow and small. Slow and small change in the load, but in the presence of. But the difference is that the presence of fast-acting voltage regulators, which are capable of changing the flux faster than the caused by the system in falling out of the system. Because there will be a, you can say, uh, when the fault occurs or when some change occur in the load, it results in a change in the voltage. And to make the voltage back to the nominal voltage, we have to change the flux of the rotor. And to change the flux of the rotor, we have to change the voltage of the rotor winding, and accordingly its current will be changed. That voltage will be changed by the voltage regulators, voltage of the rotor, because that's the DC voltage again that, and after that it's rectified. So that voltage has to be changed by the voltage regulator. But the change in this fast acting voltage regulator should be fast. To kept this uh, to track the change in the voltage of the system, because if the voltage of the system changes fast as compared to the voltage regulation this voltage regulator acting, so in that case this voltage changes fast as compared to the voltage correcting. In that case voltage will not be come to the actual value, and this also will may result in the loss of synchronism. So we can see this again the same type of stability as that of the steady state stability, but in presence of fast acting voltage regulators which are capable of changing the flux faster than the caused by the system in falling out of system. The study time for the analysis is usually between 30 to 80 minutes. So in this case, it is usually a little bit large. Now, power angle equation that I have told you in the earlier, this I will derive it. What is the value of the power at sending in and what is the reactive power at the sending in. Let's say we have a two bus system. The synchronous generator has a voltage behind the synchronous reactance, that is GXT dash. It is E at an angle of delta, and this is the current flowing through the transmission line. The transmission line has the reactance of JXL, and we have the reference voltage. Reference bus is bus 2, its voltage is V angle of 0, and it's actually an infinite bus. Infinite means it is change in frequency will be 0, frequency will not change, its voltage will not change, even if whatever be the value of reactive power or real power change. Whatever be the value of real and real power taken from the bus, its frequency and voltage will not change. So from this diagram, this I will be equal to the voltage drop divided by the reactance, that is E angle of delta, E angle of delta minus V angle of 0 divided by JXT dash plus XL. That is the total voltage. If you redraw its equivalent circuit, it will be E angle delta in series with XT dash, then connected to this transmission line. That's I have not shown. I assume that you know that. Let XT double dash plus XL is equal to X. So this I will be equal to E angle delta minus V divided by JX. This I dash, that is I conjugate, will be the conjugate of this, conjugate of this, conjugate of this. That's E angle of minus delta minus V divided by minus JX. Taking J to the numerator, it will be J times E angle of minus delta minus J times V divided by X. So the complex power at the receiving end will be equal to V into I dash, V is this value, I conjugate. So it will be equal to V into JE angle minus delta minus JV divided by X. I will take this J outside, JV by X, E angle of minus delta minus V. So I will now open it up in this real and reactive parts, that's in the rectangular form. JV by X is as it is, it will be E cos of delta minus J, E sin of delta minus V, because its angle is 0, it will be on a real term. So taking real and reactive power aside, JV by X will be equal to E cos of delta minus V minus JE sin of delta. I will stop here. I will continue in the next class. Thank you.